Okay. Hello, everyone. Welcome to Data 8, Lecture 38. Today, we're going to be talking about decisions, and then I'm going to conclude the class because today is the last lecture of content for this class. So some announcements. So there are 2 surveys that you guys should fill out. One of them is the University College of Engineering course evaluations, and one is a Data 8 final online survey. So both of those are due today at 5 p.m. So I'm going to give us some time at the end of class today to fill them out. I have the links on the slides. The links are also on our course homepage. So you can go there and check the links. Filling out the Data 8 online survey, the Google Forms one, will give you back 1 lost point on your final. If 85% of the class fills out both surveys, then the people who filled out both surveys will get back a point on their final. So there's some incentive for you to do that, and it really helps us make the class better and helps me know how I can improve as a teacher. So please fill them out and take your time and do your best in filling them out. They're due today at 5 p.m. So make sure you do that today. Okay. The final for this class will be held next Thursday from 2 to 5 p.m. Room assignments are on the Data 8 website, so you can double check the Data 8 website for room assignments. We will give you on the final the midterm study guide and the final study guide. Those PDFs are in the resources page of our homepage. So go check there for what you'll get. We'll give those to you on the exam day. You're also allowed to bring two-sided sheets of handwritten notes for the exam. Labs next week will be final office hours and final review. And lectures on Monday, Tuesday, and Wednesday next week will be final review as well. There will be 4 hours of attendance required for credit for attendance next week, but the final will count for 3 of those hours. So you only need to attend 1 of the review sessions to get attendance credit. Any other questions? Yeah.
Is the final going to be as long as the midterm?
Is the final going to be as long as the midterm? Right now, we're planning for about a 2-hour exam to be taken in 3 hours. So we'll try to give you enough time to think through each problem and work on them. But it will be longer than the midterm, about twice as long. Yes. Any other questions? All right, so today I'm going to talk about decisions. It turns out that making decisions is kind of tricky sometimes. For example, there was a study published in 1978 by the Physicians of Clinical Laboratory Results. What they did was they stood in hallways in 4 Harvard Medical School hospitals and asked 20 officers, 20 medical students, and 20 attending physicians the following question. Now, this is an awful way to get a random sample because your sample will not be random, but they kind of had a point. They kind of had a point with what they did here, so people later on replicated it with random samples. So they asked this question: if we had a medical test and it's trying to test a disease that 1 in 1,000 people have, the test has a false positive rate of 5%. So that means if you don't have the disease, it'll say you have the disease with probability 5%. What is the chance that a person found to have a positive result actually has a disease, assuming that you know nothing about the person's symptoms or signs? So they asked the question, what do you think if the test comes out positive? Does this person have the disease or not? So they asked 60 people. What they found was only 11 of them gave the correct answer. So blah, blah, blah. They found the most common answer was that the person gets a positive result, has a disease. The chance of that is 95%. So that's incorrect. There's another correct answer. Why don't you talk over with your neighbor what you think the answer to this question is? Go ahead. If you're not sitting next to someone, you can lean over or shout at them or anything. Whatever works for you. Go ahead. All of you are staring at me. All right, how about this? I'll ask you an easier question. So the most common wrong answer was 95%. Do you think the actual probability is less than 95% or higher than 95? Okay, try that. So I don't need you to calculate the exact probability. Do you think it's lower than 95 or higher than 95? Try it out now.
What is false positive actually mean? Like the person has the disease, but they're diagnosed as not having it, or like
Opposite way. All right, well, probably confused because I haven't talked to you about how to do this. It's actually lower than 95%. It's quite a bit lower. I'm going to show you that at the end of lecture today. Let's try the easier problem. So let's talk about conditional probability. So conditional probability refers to chances when you know something else has happened. So here, for example, we know that the test was positive. We want to find the chance that the person has a disease. So we can say that in probability terms as a chance that the person has a disease given that the test was positive for that particular person. Okay. So how will you try this one? So this class, or a particular class, has 60% second-year students and 40% third-year students. Half of the second-year students have declared their major. 80% of the third years have declared their major. I pick one student at random. What is more likely for me to pick, a second year or third year? How many guys think second year? How many guys think third year? Okay, talk it over with your neighbor. Try it out.
picking one student from the class, for example.
All right, so the answer here is not super hard. It's second year because there's 60% of the class. There's 60% second years, 40% third years. If I pick one student, the student would be second year with probably 60%. Okay, so let's try that. Let's try a slightly different question. Okay, so same scenario, but when I pick a student at random, I know that the student has declared their major, and now I'm going to ask the same question, second year or third year. So before, the chance that we said was that the chance of us picking a second-year student was 60%. But if we know that the student has declared their major, it changes what we think that student's year is. Think about it with your neighbor. Do you think it's higher than 60% or lower than 60%? Try it out. Okay, so let's talk about it. So I get the sense that in this scenario, I have some more information about the students. I happen to know that the student I picked has declared their major. If I did not have that information, the answer to this question is the same as the previous one. If I don't have any extra information, and I pick a student, the chance that I pick a second year is 60%. But if I happen to know that the student has declared their major, let's take a look at the numbers here. So we know that about half the second years have declared their major, and 80% of the third years have declared their major. So a lot more third years, proportion-wise, have declared their major. So we would expect, in this case, that the chance of us picking a second-year student is a little bit lower than it was before. But I'm going to show you how that works. So, same scenario. I have here a box. This box represents 100 people. Let's say I have 100 students in my class. If there are 60% second years and 40% third years, then I can split the box down the line here, put 60 of the students on the second years, put 40 of them in the third years. Then half of the second years have declared their major, and 80% of the third years have declared their major. So I can draw two lines. I can draw one right here. Oh, nice, that works. I can draw one right here, because half the second years have declared, which means that half of them have not. And I can draw one line right here, because 80% of the third years have declared their major, and the other 20% have not. So I have here 30 students who are second year and declared, 32 students who are third year and declared. Okay, so I have this box, I have the numbers. Now I'll try again. I pick one student at random, and I happen to know that the student has declared their major. Is that student more likely to be a second year or a third year? What do you think? Try it out now. All right, so how many of you guys think it's more likely to get a second-year student? How many of you guys think we're more likely to get a third-year student? A third-year student, right? Because if I happen to know that the student has declared, I'm not looking at the whole box anymore. I'm only looking at the students who have declared. So I'm looking at this box here and this box here, right? So these two boxes, the dark blue, the dark red, because I know the student has declared their major. Okay, so I'm looking at these two boxes, and I say, oh, OK, there are 30 students in this box and 32 students in this box. So if I picked a student, and I happen to already know the student is from one of those two boxes, more than half of the students are in the third-year box. And 30 of them are in the second-year box. Okay, so the chance, oh, I think I'm missing, oh, OK, here it is. OK, so the chance that I actually pick a second-year student is, I know the student is declared. So I'm looking for the chance the student is second year and declared over the chance of getting a student that was declared. Okay, so kind of stare at that, think about it some more. But indeed, it is the case here that we're more likely to pick a third-year student than a second-year student because we know that the student has declared their major. And when we split up the boxes in that way, we can kind of get that by looking at this, looking at the splitting of these students. Okay, so I'm going to take attendance. Let's do it. And I'm going to go over this one more time and actually go through the numbers and show you how that all works. I'm going to take some questions after that. And let's resume. Oops, what happened? Update. Go ahead. All right, go for it. Okay, so this idea that we can take some information that we already know. So if we observe an event and we happen to know some information about that event, that changes what we believe. That changes what we believe. Because I know the student I picked has a major, I know that there's the chances that the student is a second year or third year have changed from before, from when I did not know that information. This is described by something that we call Bayes' rule. The guy who made it was named Bayes. Okay, and the way this rule works is, let's suppose I want to find again the chance that the student was a second year given that the student is declared. So I know that my student is declared. I want to find the chance that the student is a second year. Because I know that the student is declared, I already know that. I only have to look in these two boxes here. Because I know that the student came from one of those two boxes. The student was declared, so the student had to have come from one of these two boxes. I want to ask the question, OK, I know that the student came from those two boxes. What is the chance that the student was second year? I look at the second year divided by the total amount of people in the box, which is 30. OK, I'm going to try to move my pointer. 30 over 30 plus 32, which is 30 plus 32. And I get 0.48, right? Because in these two boxes, 30 out of the total were second years. 32 out of the total were third years. So you notice something interesting about this, which is if I describe these numbers in terms of the actual probability events, what I get is this. I'm finding the probability that the student is a second year and declared, this box right here, divided by the probability that the student is declared overall, which is these two boxes added together. Okay, so the chance that the second year, given the chance that the student is a second year, given the student was declared, is the probability that the student was second year and declared over the chance that he or she was declared. Any questions about that? I saw a lot of confused faces before, and now we have no questions. Maybe if I wait a little bit longer, I can squeeze a question. All right, so you guys are doing good? Thumbs up if you're feeling good about this. Thumbs down if you don't feel so good. OK? All right, so let me just draw that same box in a couple of different ways, in a different way. OK, so we had here, I took here that box, and I drew the vertical line, and I drew the horizontal lines. I can also draw these chances in kind of what we call a tree diagram. OK, so here I have the box of 1. And what I'm doing here is I'm changing the numbers of students into proportions. So before I had a box with 100 students. Now I'm just saying that box has 100% of the students. The numbers are all the same. The numbers are all the same as we did before, just divided by 100 to get proportions. So here I have 100% of all my students. 60% of them are second year. 40% of them were third year. Okay, so 60% second year, 40% third year. Now of that 60%, half of them were declared. Half of them were not declared. Similarly, third year, 40% of them were third years. 80% of that 40% were declared. And that really small box is the undeclared third year students. All right, so same box, written in a couple different ways. The only difference here is that I'm working here with these probabilities now instead of just the box itself. So here I have 0.6 and 0.4. Here I have 0.5 and 0.5. But in reality, I'm describing the same happening. Okay. So this tree diagram has some terminology associated with these probabilities. So right here, let's walk through this. So this is a probability that I pick a second year student. This right here is a probability that I pick a declared student, given that the student was a second year. So given that I picked a second year student, half of the second year students are declared. So the probability here, this 0.5, is the probability of declared, given the student was a second year. Before we're going the other way around, before we're going probability of second year given declared, when you draw a tree diagram like this, some of the probabilities are really easy to read off, including this one. So probability of declared given second year is just 0.5. Similarly, the probability that the student is undeclared given that the student was a third year is just this probability here, which is 0.2. We have names for these probabilities. So this one right here, these two right here are called the prior probabilities. These ones right here are called the likelihood probabilities. You don't really have to remember these terms, but I'm going to be using the term prior probability in a later part of this lecture. So just keep that term in mind. The prior probability is just how many, kind of like the previous, if we had no information at all, what we would predict about a student that we pick. So if we had no information other than that we picked a student at random, our prior probabilities, what we believe prior to getting any new information, is that 60% of them would be second-year students. Okay, so Bayes' rule describes how to calculate the posterior probability. So there's 3 different words for probabilities here. They're not super important to remember. You just need to know that they exist so that when you do come across them, you can look them up really quickly and remind yourself what they are. So the posterior probability is the probability that we were trying to calculate at the beginning of this lecture, which is, let's say we take probability of third year given declared. So it's going backwards. So here we have the probability of declared given third year. The posterior probability is the probability of third year given declared. The reason why it's called the posterior is because we have our prior, which is what we believe if we had no extra information. Our posterior is what we believe if we have some more information, right? So here, this is the probability of third year given some more information, which is that the student is declared. Bayes' rule says that the probability of that is equal to probability of third year and declared over the probability of declared. In general, for any 2 events A and B, Bayes' rule states that the probability of A given B is the probability of A and B divided by the probability of B. Now, you don't need to remember that exact, what's more important to me than remembering the exact formula is if you can draw the tree diagram or draw the boxes and try to figure it out yourself, because that'll actually guide you in the right direction as opposed to just memorizing a formula. If we happen to do this calculation here for third year and declared, you're going to get 0.4 times 0.8 divided by this. So this right here is the probability that the student is third year and declared. The probability of that and that is this probability times this probability. So we have here this times that on the top. The probability that the student is declared is this branch of the tree, so this one right here, down to third year and then up to declared, plus this branch of the tree up to second year and then up to declared, because that is a chance that the student is declared. So you'll notice that these numbers here are the same as the ones that we had in the box. They're just described in terms of the probabilities on this tree diagram instead of the probabilities in that box. Or you can translate back and forth. You can just use whatever is more convenient for you. Any questions about that? Yeah, Ilya?
So that initial statement, can you just go over what exactly that means again? So is it third year or declared?
Sorry. So this line right here means given. So in probability, like when we draw notation, that line here means given. So what this means, what this reads out is the probability that I pick a third year student given that I know that the student is already declared. Yeah, sorry about the notation. So that line there means given. It's just a convenient shorthand for what the events that we've been describing previously in this lecture. Any other questions? OK, so why does Bayes' rule exist? Because when we get new information, what we believe about the world changes a little bit, sometimes by a lot. If we know the student is declared, the chance that the student is a second year is different than before. Bayes' rule allows us to calculate precisely how we change what we believe about the world, given some new information. In particular, we won't go over this today in class, but if you go on in data science and do some what we call multi-stage experiments, you can use Bayes' rule to work backwards the probability of some stuff happening. I won't go into that in too much detail today, but now we have the machinery to try to tackle this problem again. So, same problem. If we test to detect disease, blah, 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 what is the chance that the person actually has disease? So find the parallels between what this problem says and the student second year major thing that we had before, right? So here, if we had no extra information about that false positive rate, so let's say the person just did not take the test at all, we would say that the chance of the person having the disease is 1 in 1,000. Right? If we have no extra information, the prior of the chance of a person having the disease is 1 in 1,000. Now that we actually have that false positive rate, what is the chance that now that we actually have the positive result, sorry, what is the chance that the person actually has the disease? You can assume that if the person has disease, the test will always be correct. It's only when the person doesn't have the disease does this false positive rate come up. So try it out. Again, my suggestion is either draw the box or draw the tree diagram. And once you draw the box or tree diagram, it should become a lot easier trying to piece back together this probability here. Try it out now. So you should actually try it out. Draw the tree diagram, plug in the numbers. I will expect you to know how to do this. So you should at least get some practice in now. Okay, so draw it out, do numbers, find the actual number and the probability of this. Go ahead.
I know 1 in 1,000 is those having disease. The chance of not having disease is 999 out of 1,000. So that I took 5% of 999. I got this, which is still fairly close to 5%.
Oh, actually, because the false positive rate doesn't incorporate that.
Right, it doesn't. So the person has no disease, the test will always be positive.
Right.
Correct.
All right, 30 more seconds. Okay, so I'm going to use a board. Here we go. So I know that the person either has disease or no disease. Can you guys see this in the back? Is this dark enough? Is this okay? No? Okay, let me try a different marker. What about this one? This one seems, what about this red one? Nope, this red one's dead. Okay, let me try this. So we have disease and no disease. All right, and we know that the chance that the person has disease is 0.001, 1 in 1,000. The chance of no disease is the complement of that, which is 0.999. Okay, so we start here with disease, no disease. Now we split up our tree one more step, and we have positive, or a plus here, and negative test result. Similarly here, if the person has no disease, we could test positive, and we also could test negative. So here I have enumerated out all the possible now I just need to write the probabilities. So I said in this question that if the person has disease, the test will always be positive. So the test will always be right. It'll always say this is 1, this is 0. On the other hand, if the person doesn't have disease, then the false positive rate is 5%. So the chance that the person doesn't have a disease and the test does positive is 5%. 0.05. 0.05, which means that the chance of this is just 1 minus 0.05, 0.95, like that. All right. So once I have this tree, now I can just find the probability that the person has disease given that the person was positive, which is probability. I have it on the slide. Let me just do the slide. OK, so I have this tree, okay? The same thing that I drew on the board. So the way I do this is I'm finding the probability that the person has disease given the test was positive, which is the probability of both those things happening divided by the chance that the test was positive. So the chance that the person had disease and tested positive is 0.01 times 1, because I'm doing the multiplication rule here. That goes on top. And the chance that the test was positive goes in the bottom. So the chance that the test was positive is either this branch of the tree or this branch of the tree. So I multiply these two together and add up this times this. I put that on the bottom. And I get back a surprising result, which is 2%. So even though my test was pretty accurate, in that it only had a 5% false positive rate, and if you had a disease, it'll always be right. Even though that's true about my test, if I make the test and the test is positive, what I think about the person is that the person only has a 2% chance of having the disease. Kind of strange. Are there any questions about doing this? OK, so when in doubt, what you want to do is you just want to take your events and draw them out in the tree diagram. Then you ask me, what if I put plus and minus here and a disease and no disease here? You get the same thing. But you would notice that some of the probabilities will be pretty hard to write. Right? So if you do plus here and minus here, you won't exactly know how to do the split here. And you can try it out on your own, and you'll find, OK, the problem doesn't actually give me the chance of a positive or negative test result. I have the chance of a disease or no disease. OK, so when you try it one way and you find it's hard, try writing it the other way. Usually, that'll make your tree diagram a lot easier to write. Figure out what you want to calculate. Any questions about this? Yeah, Kevin?
So basically what this out of is the overall probability that the test will come out positive.
Sorry, repeat that?
So the denominator of the fraction is the probability of the test coming out positive.
That's right. So the probability that the test is positive. Is this my good marker? No, I put it over there. The probability the test is positive, so I'm going to write it up here, which is is this right here plus that right there. Because those are the two ways I can get a positive test result. I add them together to get the overall probability that the test was positive. OK. All right, so we did some calculation here, but my takeaway that I want you to get from this is this chance is really low, only 2%. The test was pretty accurate, right? So if we go back to the test was pretty accurate. Why is the chance so low the test is accurate most of the time? It turns out that it's because of this right here. Because it's so rare for a person to have a disease, and you can try this out, and I'm going to show you how that works in a second. It turns out that because it's so rare for this disease to occur, even though my test is super accurate, I'm still, after the test happens, I'm still like really unsure about whether that person actually has disease or not. I'm doing a little bit better than before. Okay, so before I thought that a randomly picked person from the population would have a 1 in 1,000 chance of having the disease. Now I think that chance is 2%, which is more than 1 in 1,000. but it's still not very high at all. It's still not very high at all. It's only 2%. Yeah.
So what the original question was asking was, given that the test came out positive, what are the chances that the person has the disease?
That's right. So probability of disease, given the test was positive, a positive result. Okay. And so when it comes to making, so my takeaway from this is that it turns out that Bayes' rule is, we kind of use it in the back of our minds when we make decisions, right? So for example, let's see. If I'm trying to decide whether or not to drink tea, well, that probability is 1. So that doesn't help me. If I'm trying to decide what apartment to move into, right? I'm trying to decide what apartment to move into or who my roommate should be. I take into account a bunch of different factors about what I'm looking for in an apartment, right? So I'm like, okay, I want this apartment to look like this. I wanted to have like at least 1 bedroom, hopefully. I want to have at least 1 bathroom, hopefully. A kitchen, hopefully, right? And what happens is I have those beliefs. When I actually go see the apartment, I'm like, okay, this apartment doesn't have a bathroom, but I can use a porta potty, or you know what I mean? Like if you actually go see the apartment, then you can say, okay, now I'm going to change what I think about the probability of getting this apartment based on what I see. So I have some prior beliefs, my priors, and once I actually see that what happens, I change what I think, right? I make a new decision based on some information. It turned out that Bayes' rule is like the mathematical quantification of that process that we happen to do all the time in our daily lives. And in particular, when it comes to making decisions, we're dealing here with what we call subjective probabilities, which sound weird because how can probabilities be subjective? But it turns out that in our case, they can be. So there's 2 ways of viewing probabilities. One way is the frequency with which this thing will happen in repeated trials. So if I roll a die, I expect that out of 1,000,000 rolls, 1/6 of them will be 6s. That's like the frequency view of probability. The other view of probability is my degree of belief about something. Okay, so in the prior example, my belief that a randomly selected person would have a disease is 1 in 1,000. Now that number didn't come from like data. It didn't really come from me asking. It came kind of from data, but I'm not super sure about that probability, right? Now 1 in 1,000 was an important number in our calculation, but I'm not super sure about it. Because if a person comes into the doctor's office and actually gets the disease, or actually gets the test like prescribed, so the doctor says, okay, I think you should get this test, the chance of that happening is probably not the chance that a randomly selected person from my entire population has a disease or not, right? So what I'm saying here is, originally I said the disease is 1 in 1,000. So out of everyone in the whole world, 1 in 1,000 of them will have the disease. But when I think about that, and I think about the people who actually get the test, I say, okay, well, if they're actually getting the test and going into the doctor's office, the chance that they actually have the disease in that case is probably higher than 1 in 1,000, right? Because they actually think that something is wrong. Probability there, that 1 in 1,000 is my belief. It's what I think is true about the world, but it can change as well. It's a subjective probability. In particular, we use that subjective belief to do some calculation, but it turns out that our calculations change a lot if our beliefs change as well. Our prior probabilities change. So if I draw the same tree as before, the same tree, disease, no disease, positive, negative, and all I change is these prior probabilities. Before, the prior probability was 0.01. 1 in 1,000 people had the disease. What I'm saying now is, okay, if you're actually getting the test, I think you have a 1 in 20 chance of having the disease. It's a lot higher than it was before because you're taking the test. I think it's not super high. It's not like 80%. I still think it's 1 in 20, but it's higher than it was before. So 1 in 20 have the disease. 95% of them don't. Okay. If I repeat the calculation I did before, I get a very different probability. So I'm not going to go through the steps of how to do that. You can look through the slides again and just work out the numbers. But if I repeat the steps, I no longer get 2%. I get 51%. So just by changing my prior beliefs, my priors here, about what I think the chance of a person getting the disease or not, I get a very different decision. Right, so here, this 51% says, okay, if you got the test and it came out positive, I think more likely than not that you have the disease. Now, I'm not super sure, right, because 51 is not like really great, but I would say, okay, chances are like more likely than not that you have the disease. In the previous case, if I was still under the assumption that 1 in 1,000 people have the disease, I would say, okay, the test came out positive, but I really don't think you have the disease. Yeah, Elliot?
So a bit of a digression, but in the medical field, is this sort of the approach they apply when they're treating patients?
Yeah, so nowadays, so this study, oh darn it, okay, so it's kind of back far. Let me go back here. Wow, it's really far. Okay, so this study was in 1978. And they did this study in 1978, and they were like, okay, you guys like don't really know how to think about probabilities. Before, people were thought that if the test was pretty accurate, if the test came out positive, you almost certainly had the disease, give you a bunch of medicine. But it turns out that it's not entirely true, right? Even if a test is really accurate, because that disease is not common, we still don't really know. And so they said, okay, guys, like you need to sit down and like teach people how to think about probabilities better in the medical field. So over the course of the next like couple of decades, they incorporated it into curriculum and other things so that people and doctors actually took this stuff into account. So nowadays, if you actually go and like get a test for a rare disease, what they should say is, okay, it came out positive, you should get a couple more tests, just to make sure. So as you get a couple more tests, you can actually work out the probabilities there. That probability of you having the disease, given that you had multiple tests and they all came out positive, gets higher and higher. Great question. So the priors matter. And in fact, they matter in a bunch of different scenarios. So in this case, so there was a story some number of years ago where so in physics, they have what they call particle accelerators. And what they do is they make things move really fast, and then they smash them together. Sounds a lot of fun. And what they found, one day, some researchers at a particular particle accelerator, let me see if I can get what it is. Might be in my notes, but unfortunately they don't show. Apparently this opera collaboration based in Italy reported a very unusual thing, which was that they found that some particles are going faster than the speed of light. Okay, so they got some data, and they were like, turns out that when we accelerate these particles, they went faster than the speed of light. Now, for those of you who know physics, it's impossible, or the laws of physics state that it's impossible for particles like the ones that they were doing here to go faster than the speed of light. But what happened was, they kind of released that data because as researchers are kind of like, okay, we should just release all the data and all the results that we get. So they released it. And what happened was the physicists were like, okay, this is obviously a mistake in the machine, right, or in measurement or something here. Because I know that I believe in the laws of physics, and the laws of physics state that this is impossible. So it must have been something broken with the machine. And journalists, on the other hand, said, oh, seems legit. And so they're like, wow, like amazing, new physics breakthrough. Like we found particles that go faster than the speed of light, which implies that like time travel is possible, apparently. So they're like, time travel is possible, everyone. And then everyone was like, oh my gosh, what happened? So we had two groups of people that have very different conclusions from what they observed, right? So they observed some event, particles going faster than the speed of light. Two groups of people had very different reactions. But if you think about it in terms of this like prior, likelihood, posterior kind of framework, it actually kind of makes sense. So you look at the journalists and you're like, okay, these journalists are silly because they reported something and that wasn't true. But if you think about it in terms of their beliefs, so the physicists have a lot of prior belief in the laws of physics, right? They've like studied physics their whole lives. They believe in the laws. They've done experiments to personally like verify those laws. And because of that, their prior beliefs that the laws of physics hold were very, very high. The journalists, on the other hand, probably had some lower prior probabilities there, right? They looked at that and they were like, okay, all I know about physics is what some physicists told me way back when. That physicist could have been, like who knows, in a couple of years, our theories can change a lot. So maybe those physicists were wrong. And with some pressure from like a journalistic company, maybe they'll have some more pressure to write an article like that. But what I'm trying to say is, you can observe the same thing. Both journalists and physicists observe the same thing, that the Gaussian particles fashion the speed of light. Both of them had different outcomes. And they could have made those outcomes even if they were both very rational people, both rational things, right? Based on what we saw here is that if we change our prior probabilities, our conclusions change a lot. So even if we observe the same thing, positive test result, depending on what our prior probabilities are, which are subjective, right? These are subjective because we don't really know. Depending on what those are, our conclusions change. And so it's possible, and probably pretty likely in this case, that it's just because of their prior beliefs in the physics or in what they heard secondhand or all of that stuff, that they're both acting rationally, that they're both like intelligent people, journalists and physicists. But because of their prior beliefs, they came to a different conclusion. And indeed, if you try out this rule yourself with some like different like things, so another thing you can try out is, let's suppose that I go to New York and I come back and I'm like, wow, I just saw some guy who could predict 100 coin flips in a row. That person must have like extra spiritual powers or something, right? Who can like predict the future. And you can actually run like the Bayes rule thing, given some prior probabilities about this extra, what is it, like extraordinary powers existing versus not, and you can do that, and you'll find some probability, and that probability will probably say something like the chance that the person has like extraordinary powers based on observing 100 coin flips is really high. But if you factor in the prior probability that I'm crazy, then what you'll find is that you'll find it's more likely than not that I'm crazy, right? So a similar thing happened here. The physicists saw the result and they're like, okay, turns out the machine's broken. But based on your priors, you'll get different conclusions. So your priors matter. And to recap what we discussed, we have Bayes' rule, which lets us calculate conditional probabilities. When you're actually working with these problems, it's really helpful to draw that box, to draw that tree of events to help you make some conclusions. And when you're making decisions about the world or looking at other people's decisions about the world, it's important to account for the priors. Okay, so account for your priors. Say, okay, my priors are this. That person's priors could be just different. And make sure you account for those beliefs when you're trying to make decisions. Any questions? All right, well, I think a round of applause is in order because we have just finished all lectures in Data 8. Woohoo! Congratulations. So we're done. What's next? So it turns out that Data 8 is what we call like a very introductory level class. So we talked about a lot of different topics. We don't go super deep into each one because we want to give you a sense of what data science is all about, just an introduction to the entire field. If you want to actually do more data science in real life, you want to get some more skills. In particular, you want to get some programming skills. Okay? In this class, we don't write large programs, but in the real world, you'll probably have to do that because you'll be working with larger and more complex models, larger and more complex data sets. So to get that know-how, to get the skills you need to develop larger programs, there are some classes that you can take. Okay, so there's CS61A at Berkeley, which is going to be taught both next fall and next spring by Hilfinger and John De Niro, who came in to guest lecture a couple days ago. So if you liked him, you'll want to take CS61A. Okay? They teach core computing concepts, so you learn how to write programs. You do a lot of program writing. You learn how to do some declarative table processing using SQL. About 1 unit of CS61A overlaps with Data 8. So in 61A, they'll teach you about functions, the same stuff that we learn here. They'll teach you about for loops, the same stuff we learn here. So the first quarter of 61A is about the same as the concepts we learn here, but the last 3/4 of it are very different. There's also a connector class called CS88. We're not sure whether it's going to be offered in the fall or not, but you can check the website. Oh, I don't have the website on the slides. All right, here. But you should check this website for more information about it. It'll get posted here when we're done. So the website is data. Darn. I'll just do my best here. Data.berkeley.edu. .edu. So data.berkeley, I'm going to do a B here, .edu, do an E for edu, okay? That website has all the information or the latest news about the data science program, including which classes are going to be offered or not. So CS88, we don't know what it's going to be offered, but if it is, here's what you should know about it. It's about like the middle chunk. It covers about the middle chunk of CS61A. So data 8 covers about 1/4 of CS61A. CS88 covers about the middle half of CS61A. It goes like it has a data first perspective. So it teaches you the same concepts in 61A, but in a context of working with data as opposed to just writing programs. If you want to take CS61B, the data structures class, which is normally considered the second class in the Intro to CS series, you can continue on to 61B after taking data 8 plus this connector, CS88. So CS88 is kind of an alternative to 61A for people who've taken data 8. All right. Any questions about that? OK, I'm going to keep going. So you want to learn some linear algebra. So in this class, we work a lot with arrays of numbers, right? A lot of our data sets come in like a tabular format, a rectangular format, and a lot of times you work with numerical data. It turns out that there's a lot of mathematics behind working with tables of numbers. Kind of interesting, right? It turns out there's a lot of interesting, very unique mathematical results that come out of working with just tables of numbers. And linear algebra is the field that describes the mathematics of that. In particular, Math 54 at Berkeley teaches linear algebra and differential equations, but it has no computing. So Math 54 is considered a prereq for a lot of other classes at Berkeley, including more data science classes. You'll probably have to take it at some point. Or you can take E16A, which teaches linear algebra in the context of working with circuits. And in that class, they do some computing using Python and Jupyter. But it's in the context of working with circuits. You'll also want to learn some probability. So as I mentioned before, probability describes what happens in the world given some prior beliefs or given some model about how the world works. In particular, a class called Prob 140, which was piloted last semester and will be offered again in the spring, teaches these probability concepts. It's listed as Statistics 140. Some members of the course staff have taken it. So if you have Catherine or Arvin as one of your TAs, they both have taken Prob 140, so you can ask them all about it. And in Prob 140, you use computation in kind of a similar way as data 8, but in a probability context. So you do simulations. You use a computer as a tool to learn about probability. There's an alternative to Prob 140. So Prob 140 won't be offered next fall. It'll be only offered in the spring. There's a SAS class called Stat 134, which teaches almost exactly the same material as Prob 140, but in a mathematical way and not a computing way. You'll still have to learn the math in both classes. Stat 134 does not have Jupyter notebooks. Prob 140 does, but Stats 134 will be offered again next semester while Prob 141. So take that into account as you plan your classes. All right. Next, we have statistical inference. So statistical inference says, given my sample, what can I say about the model? So probability, once here's my model, what can I say about my sample? Inference goes the other way around. We've done a bunch of inference in this class with hypothesis testing, with confidence intervals, with regression inference. And if you want to know more about that, you can take Stat 28, which is statistical methods in data science. It won't be offered again next semester. It'll be offered again in the spring. And they teach in the language called R, which is a popular language of choice in data science and by statisticians. It requires and directly extends data 8, which is good because we've just finished data 8. Okay, so Stat 28 is an option if you want to know more informational techniques. Stat 135, the upper division stats class, also covers the same kind of topics. It requires Stat 134 or 140, so it's considered a slightly more advanced course. And it has no computing applications, but you'll learn all about statistical inference. Finally, we have data science and machine learning. So the core idea here is that data and not logic alone determines the behavior of programs. We've seen this a lot when working with classifiers. In particular, DS100, the upper division data science class, will be offered again next semester and in the spring. It'll be taught by this professor named Joey Gonzalez. It's listed as Stat C100. I'm going to be the head TA for the class in the fall. So if you couldn't get enough of me this summer, you want to see me again next semester, you're going to take Data 100. It requires 61A and Data 8, and it also requires linear algebra as either a prerequisite or concurrently with the class. Okay, so it's an upper division class. We're going to do a lot of the same stuff in Data 8, but in a more advanced way, working with larger data sets, working with more machine learning models, all that stuff. It's going to be taught, but you're going to need some more background for it. We're also creating a new upper division data science class. We don't know what the number is. It might be 101. It might be 102. We're thinking that it might be piloted in the spring of 2018. It's designed as another follow-on course to DS100 with more techniques and more data science. DS100 will require Prob 140. So it'll require you to know more probability theory. Whereas 101 and 102 will require you to know some more probability, whereas DS100 does not. So plan accordingly for that. There's also CS189 or Stat154 or IEOR 142. These are all classes about machine learning. So if you like the classification stuff, you want to do more of that prediction, you'll want to take one of these classes. Most of them require some probability and linear algebra because as you go farther into machine learning, you'll just have to have the background necessary to kind of learn about the different statistical models that they use for data. All right. We're probably going to release more machine learning courses, but as of right now, these are like the safe options you can take. Any questions about all this stuff? OK, so because there are no connector classes in the summer, if you're still around in the fall, I highly, highly encourage you to take at least one connector class. You can click this link here. Go to data8.org/connector. You'll find a really nifty-looking website that looks like this. And these classes are 2-unit classes taught by professors from different departments all over campus. They've all come together and said, OK, I want to teach data science, but how it applies to my field. Whether it's legal studies, statistics, information and ethics, cancer, cog-sci, time analysis, geography, history. There's so many, neuroscience. There's so many different connectors. They're all really interesting. So if you're around in the fall, I highly, highly encourage you to take one because data science is meant to be applied. Right? It's meant to be applied. You learn the techniques so that you can use them in real life. And to use them in real life, you need to have a reason to use them. Connector classes are a great way to get a sense of, OK, here's a field. Here's how data science fits into the field. All right, let's talk about degrees. So it turns out that we're planning to create a data science major and minor. There's been a lot of meetings and discussion about it. And basically, a bunch of people are on board. So a bunch of faculty, a bunch of administrators are on board with creating this data science program, department, degree program, whatever you may call it. We have just recently selected a dean, an interim dean for data science, who is Professor David Culler from the CS department. Both DAS and EECS departments now have a data science curriculum committee. And a data science major and minor, we're hoping, will be available as early as spring of 2018, which means that if you're graduating in the spring of 2018, it might be possible for you to graduate with a data science major or a data science minor. So I would say don't really plan for this because we don't know what might happen, but we're going to try to make it available in the spring. Cool. So here are my guesses about what that major might entail, or what you might need to take in order to graduate with the data science major. It's totally unofficial. Don't quote me on this. I'm going to be wrong. But here's my guess. Okay, so in the lower division, I think that you'll probably want to take Data 8, some calc, linear algebra, 61A program like computing. You'll probably also need data structures as well, CS61B. Okay. In the upper division, you'll almost certainly want to take Data 100 plus Data 101 when it's offered. There should be a plus here, but it's a slash. Oops. Let me fix that. Let's fix it now. Got it. No. Okay. No, I was so close. Okay, there we go. Keep it on one line. All right. So lower division classes, this is what I think. Upper division, almost certainly data 100, almost certainly data 101 when it's being offered. You'll almost certainly need probability, almost certainly some machine learning. And then we'll probably require you to do some breadth classes in different departments just to make sure you apply some data science and emphasis classes and social context and ethics. So this is what I think. You can take a look at this on your own time. But this is what I think will probably go into a data science major. For data science minor, I suspect that it'll probably be data 8, linear algebra, C61A, and probably DS100 and stats. So I'm thinking those will be required for the minor. But again, entirely speculative. I have no idea what's going to happen, but that's my guess. Any questions? Yeah.
Can you go over what you think the minor might do one more time?
What I think the minor might be. So I am quite certain it's going to involve both data 8 and data 100, at the very least. Quite certain. I'm quite certain it'll involve linear algebra and 61A because those are prerequisites for data 100, so probably required as well. And you'll probably be required to take some calculus and some probability. But I don't know exactly what goes into the minor. They might do more classes, they might do less. But almost certainly data 8 and data 100 with the prerequisites for those classes. Any other questions? Yeah.
You said 101 was going to be piloted in the spring.
Yeah, so that's what I think might happen. Who knows whether they'll actually get the material ready in time. But they are thinking about it and thinking about what might go into that class. So I think the current plan is to get it ready in the spring, but it might not be offered until next fall, until the fall after that. Yeah. Any other questions? Yeah. So is there any difference between Stat 133 and Stat 134? So Stats 133 is pretty much programming in R for statistics majors. So you'll learn a lot of programming in the R language. R is in a language like Python. So you'll learn a lot of that. In terms of the actual statistics concepts, I would say there's probably not as much. So I would say if you've taken data 8, you probably don't need to take Stat 133. But I could be wrong because there might be stuff there that isn't covered in data 8. So you can double check the syllabi for both classes and take a look. But Stat 133 is pretty similar, I think, in concept to data 8. Stat 134, on the other hand, is about just like probability theory. So about like chance events, likelihoods. They go over a bunch of different topics there. So it's a lot more mathematical. And I don't think Stat 134 involves any programming. Yeah.
For CS189, apart from the math background probability and linear algebra, do you need to know more programming, like have more programming experience?
Yeah. So CS189 requires a bunch of programming. You will at least need to take 61A and probably 61B in order to want to succeed in that class. Yeah. It's CS189 is a pretty advanced undergrad class. So I would say take a look at the prerequisites and make sure you have them before you take the class because it's pretty challenging. Mm-hmm.
What's one of the things that makes it so difficult? Because I've heard it's pretty challenging. So
why is 189 so hard? It's because in 189, they don't do a whole lot of review. The concepts they expect you to know, they just kind of go into it. And from like the very first day, you work with a lot of matrix algebra, matrix differentiation. So they assume a lot of math background, and it turns out that a lot of CS students don't have a whole lot of math background. So that's why a lot of CS students find it difficult. Yeah. Mm-hmm.
What are some example courses starting from machine learning and below your chart, like maybe even some personal experience, like stats 135? Part of that?
Yeah. So these would be classes like Stat 135, like more statistics, more probability, or more computation, like CS 186. which is databases, or Sys162 operating systems. I don't know about that one, but more classes in either department that go in more depth than the classes here.
Like for the next one, what is
7 units of emphasis courses, it'll probably be time in classes in other departments that make use of data science. That's what I think, at least. So the main context, as in like in geography, how to use data science, or in astrophysics, how to use data science, all that stuff, or theory, which is kind of like, I guess, a theory behind all of that as well. Yeah, not super sure about the theory one, but chances are other departments are trying to get out classes that make use of data science in their disciplines, and we'll probably require that for the major when they're available. Yeah.
Could you talk about how Math 54 is applied to like the upper division stats and probability classes?
Yeah, so how is linear algebra useful? So linear algebra is useful because linear algebra, linear algebra describes like matrices of numbers. So when you have like numbers arranged in a tabular format, and it turns out that when you're describing mathematical operations on like tabular data, you can either write out each expression individually, or you can, so for example, in Python, if I didn't have a NumPy array, I could take every single number in some like amount of numbers and add 1 to each one. Alternatively, I could just put it into an array and add 1 to the array, and just do that. So in a similar way, learning some linear algebra allows you to describe like really complex mathematical operations, but in a really succinct way. So that's why you really want that for when you start getting into more complicated data classes, because you work a lot with like kind of algebraic numerical manipulation that involves lots of numbers at once. Yeah. Okay. So what is data science? So when I actually first got involved in the data science program, I totally thought data science was just another buzzword. You guys hear those buzzwords like big data, machine learning, like blockchain. I don't know, there's like a ton, right? Like just distributed computing, cloud computing. I thought it was just another buzzword that people used to describe something that wasn't that special after all. I thought data science was just like a weaker form of machine learning, or just like another word for like CS plus stats, but they want to make it sound cool, so they came up with this random word called data science to describe it. And it turns out that I was kind of wrong. Not super wrong, but kind of wrong. So it is a buzzword that people use. And it is a word that people use and use to mean a lot of different things. So if you go actually into industry and look at data science positions, you'll notice that basically every single data science position will require different things. And that's because it's a very new field. It's a new field because we have so much data. And we have so much data only recently. So only recently, in the past couple of years or so, with the internet monitoring every move you make, with like different instruments like in science that can grab and capture a lot of data at once, it's only because we have so much data that traditional statistics doesn't really work anymore. Like the old tools that we had are not sufficient to work with huge amounts of data, and you need some more computing concepts. So it actually came out first because of industry. I believe Amazon was like one of the first companies to actually coin the term data science, because they had so much data and they had no one who knew how to work with it. They had computer scientists that could work with the computers but didn't know how to draw conclusions. They had statisticians that could draw conclusions but could not get the numbers, like the data in place to actually draw any conclusions at all. And so they're like, okay, we need people with a new skill set. They coined the term data science, and it kind of stuck with everyone ever since. So it kind of came from industry, but it now has a lot of applications in all the different domains. So in particularly in research, nowadays research tools capture a lot of data. So if you study, for example, like neuroscience, and you go like do brain scans, you get tons and tons of data from like just one scan. If you study astrophysics and study like how things move in outer space, there's like tons and tons of data associated with that. Lots of different fields now have too much data and they don't know how to effectively work with it. And that's why data science has really caught on, not only in industry, but also in academics as well. That's why there's so much support in the school, at least UC Berkeley, behind the data science program. So indeed, it is kind of like CS and stats, but in a way that combines both those fields together to be more useful than either of them learned separately. In particular, in data science, we emphasize using computation. Computation is often the only tool that we have when working with tons and tons of data. You can write out data by hand and plot them by hand, but who wants to do that when you have a computer? Okay. And in particular, once we have that data and we use good statistics to draw conclusions on it, what we get is, because our data is in place and our process is good and described completely, people can agree on both the evidence and the way it was created. It's a way for us to communicate results and conclusions to other people that may or may not be super proficient in either computer science or stats, a way of communicating results to other people that may not even know what data science is. Okay. So if you remember nothing from this class, you should remember this. How do you analyze data? State your assumptions, choose your methods, visualize first, and then quantify. And then when you're done with all of that, make sure you can communicate that. Okay? It's no use if you do all the math, but you can't talk to other people about it because you'll be alone with all your results and no one to listen to you. So make sure you know how to interpret it without jargon, interpret it in a way that people can find reasonable and can understand. Okay. So how not to analyze data? Quantify only. You want to do all three of these. You don't want to do just quantify. You'll get misled. In particular, if you're analyzing data in 2017, you should probably do both of these things using computation. This is data science. In Data 8, we've covered a lot of different topics. Okay, we've come a long way. It's only been 7 weeks, but we've covered tables, working with distributions, sampling and resampling, parametric and non-parametric prediction, which is just another fancy word for confidence intervals or looking at normal distributions, and machine learning. We covered a lot of these different topics, but you notice that in this class, we left a lot of questions unanswered, right? So a lot of times in this class, I said, OK, there's a reason for this, but I'm not going to describe it. There's a reason for that. I'm not going to describe it. There's a way to do this, but I'm not going to cover it in this class because we don't have the time. It's an intro class. So I don't have the time to go over everything in as much detail as I want. That's what upper division classes are for and advanced classes are for. But in this class, we get to cover a whole lot of things and give you a taste of what it is like to do data science. It involves computation. It involves statistics. It involves prediction, machine learning. All these things kind of combine so that you can step out of this class, hopefully, and understand how to work with numbers. And for me, I really enjoy this class because it brings together people from like all sorts of different places on campus, all sorts of different places around the world. We have a lot of international students. And we have a lot of people from different backgrounds, people who bring their different perspectives into this class. And we can all come out, hopefully, thinking, OK, I feel more comfortable with numbers. I feel more comfortable interpreting stuff in a newspaper. If someone says to me, 67% of chocolate eaters had lower heart rate, I'll know how to interpret it. Causality. And so for me, like the reason why I really enjoy this class is because numbers are everywhere. Numbers are everywhere, and people use numbers to make claims all the time. And for people to understand, like, OK, this is a good conclusion. This is not such a good conclusion. That kind of skill is super valuable and will really help you make better decisions. All right, so I'll end Data 8 with some life advice. Of course, my life advice involves some data science. So here we go. My first piece of advice is a little bit of slope makes up for a lot of y-intercept. So here I have a graph. This is a very scientific graph here. So if you start here at the bottom, let's say you start at the bottom and someone else starts over here. Even though you start really far apart, if you have a higher slope, over time, you'll get more of something good. That's kind of what I'm trying to show here. You get more of something good. And what I'm trying to say here is that sometimes, and especially for us, because most of us are kind of early on in their careers, most of us have big dreams and all that kind of stuff. A lot of times we look around and we compare ourselves in the present moment. We look around and we're like, okay, I'm not as good as this person right now. I'm not as talented as this person right now. I'm not all of this stuff. But in reality, you can get there if you focus on your growth. If you focus on the rate of change, your regression line, your slope, whatever you want to call it. If you focus on that stuff, it's oftentimes more productive and oftentimes just better mentally for yourself than just comparing yourself at the present moment in time. A little bit of slope makes up for a lot of wireness stuff, especially in the long run, especially because we're young and we have bright futures ahead of us, hopefully. Second piece of advice is the same data with different priors result in different posteriors. So I went over this today. What do I mean? What I'm trying to say here is that two people can have very different conclusions about something based on their prior beliefs. They can both be completely rational. They can both observe the same thing happening, but they can come to a very different conclusion because of their prior beliefs. And so when you look at another person, so for me, the challenge is when I talk with another person and we have a disagreement, it's difficult for me to kind of understand their point of view because I think, we went through the same stuff together. We should have the same conclusion. But what I'm not accounting for in that argument is the fact that we might have different priors, might have different prior beliefs. And I think for me in particular, personally, so for those of you who are in tune with American politics, you'll know that American politics recently has been kind of in a state of disarray, confusion. And I think for me, when I first heard about the results of the presidential election, I was like, I can't believe it. Who are these people? How could they be so how can they be rational human beings if they, wanted to vote a certain way in a particular election? They vote differently from me, right? Because I'm rational, I'm right? And I think after thinking about this, so I was doing some data science one day, and I was like, maybe they just have a different prior. And it's important to understand that. I think I realized it's important to understand that, so I don't just think these people are irrational. Different backgrounds, different history, different things that happen to you in your life shape your prior beliefs. And because of that, they shape your conclusions as well. Finally, the classifier is more important than the prediction. This makes sense in a machine learning context because we want to make sure your classifier is good. If you just focus on one particular prediction, it won't really help you make a good classifier. And what I'm trying to say here is that oftentimes, at least for myself, I'm very results-oriented. You guys know what I mean? Result-oriented. I do something, it turns out good, it turns out bad. I lecture up here, I go back home, and I'm like, that was a good lecture, that was a horrible lecture, why am I here? And what I'm trying to say here is the results of what happens, sometimes you don't have complete control over, right? I try something out. I try my best, I work hard, I do everything that I can. It still doesn't work out the way I want it to. And for me, it's very easy to get fixated on that result. To say, that was terrible. I should have done better. Why was I so why am I such a terrible person? Why am I lame? Why am I so uncool? All those thoughts kind of go in my mind. And I think one day I sat down, I was like, okay, I can't do this anymore. I need to think about a different way of looking at life. And I thought of this, which is the classifier is more important than the prediction, because we do some classification every day, right? I look at you guys, I'm like, okay, I see with my eye shapes, carpet, people that I know. Do some classification there. I go on the street. Should I go buy a smoothie or not? Classification there, right? And it's more important for me at least, to do some introspection to think, okay, my mentality or the way I approach things is more important than the actual result of whatever it is happens. I don't have complete control over my results. And trying to get complete control over my prediction or my result, trying to get 100% accuracy is not always feasible. But instead, if I just do the best I can and focus on the classifier, focus on myself rather than my results, I'll be a happier person. And So I have an interesting story about how I got started in this computer science business. So drink some water first. So back in high school, I was really into chemistry. Any chemistry lovers here? Got a couple? Hello. I was really into chemistry. And I thought, I'm going to study chemistry for the rest of my life. So I applied to all my colleges as chemical engineering, as chemistry, as who knows what other chemistry things there are out there. I wanted to do chemistry. And what happened was in the senior year of my high school, my friend introduced me to these websites called edx.org and coursera.org. Have you guys heard of those? Some nods, some question marks. So those websites are where a lot of different universities have put their classes online for free. So you can go to the websites. Berkeley has put up classes. MIT has put up classes. A lot of different colleges put classes on these websites for free. And I saw that, and I was like, my senior year of high school, I didn't have too much to do. So I was like, OK, seems all right. I'll just take some classes here and see how they go. So I took a CS class. I really liked it. Took some more CS classes. Really liked those. And before I knew it, I was taking like 8 classes at once. And I had a boatload of homework from all my classes, like projects, problem sets, like all that stuff. I had a boatload of projects and work to do from those classes, and no work at all for my actual schoolwork. And I sat down one day and I'm like, this is crazy. Like, why am I so insane? Like, why am I doing this? And I think it was because I like sat there and I was thinking to myself, and I was like, seems kind of crazy to do this, but I want to do it. Like, why do I feel like I want to do this so much? And I think it was because for me, I found out that I actually enjoyed learning about things, which is like a really great realization, right? Everyone knows that. But I think for me, at that moment in time, because I was a senior in high school and I was applying to colleges, and I was like, OK, college, that for me to actually like sit down and say, OK, I'm going to learn about this because this is cool, because I want to learn about it, and not because someone else is telling me to do it, not because I'm getting a grade for it, not because of other external factors that may go into whatever it is that I do. Just the fact that I was sitting there and doing something that I wanted to do was quite an epiphany for me. And I realized that for a long time, I did not enjoy learning, or I thought I didn't like it. Like, you go to school, you get bad grades, and you're like, OK, I hate learning, I hate math, I hate English, I hate everything that I do bad in, because I want to do well. And for me in that moment, I was like, well, honestly, like, even if I fail this class on edX, it doesn't affect me in any way. But it doesn't really matter, because I can take more classes, I can keep learning, I can just keep going. And it was kind of like a big wake-up moment for me, because I didn't know that I liked learning for a long time. And it's really unfortunate to me that a lot of times in the school system or in education, we kind of get that like initial like, I like learning moment kind of beaten out of us by the system, right? Because we get really focused. There's so many things that want your attention. So many people telling you have to succeed and do well and like measure up to a standard that they put. And a lot of times, like, we forget that sometimes it's just fun to learn, and you can have a lot of fun learning and not worry so much about the results of that learning, as long as you find it interesting and useful for yourself. And so I want to leave you with that this class might not be important for you in the grand scheme. It might be really important for you in the grand scheme of things. But what's more important to me is that you walk out of this class and you're like, OK, I enjoyed something about this class. If not this class, some other class. Fine. I won't take it personally, I think. OK, so I enjoyed something about this class. I enjoyed something about another class. What do I enjoy? Let me just do what I enjoy and not worry at least for now about the results of what I enjoy, because learning is fun. That's all I got. So you can stay here and take some surveys. So I have here, if you recall, at the beginning of class, I made an announcement. A lot of you guys walked in late, so let me repeat my announcement. 2 surveys. One of them is the final survey for this class. You get 1 lost point back on your final if you fill it out. This survey right here is a College of Engineering survey. You'll also get another point. So if 85% of the class fills both surveys out, the people who fill out the surveys get back 1 point on their final. Okay, so you can either stay here, take some surveys, or chat with me on stage. I wanted to end by saying thanks a lot for a really great summer. I had a good time. I hope you had a good time. It was great to get to know a lot of you guys, and I wish you the best in everything. Thank you. So take some surveys.